All right, I want to take a moment to kind of review the tools that you have been given. Now, these are circuit-based tools, but in this class, these tools are things that are supposed to be useful to you, right? One of these tools is resistive sensors. By mean, I mean something that its resistance is a function of the measurand. And we started with thermoresistor, then I did thermistor, and then we did potentiometers, right? So that is a tool, one tool that you have available to you. Okay. Another tool that you have is voltage divider. Right? That was a good tool, right? I'll just put a little picture of it here. That's this tool where you now have a V, and let's call it V measurand. Right? A voltage divider is a tool that you use your resistive sensor in to get a voltage that changes with your measurand. That was a tool that you had, right? Along the way, so I gave you an equation for that, and we did rely on, let me try this other marker here. We did rely quite a bit on Ohm's law, didn't we? V equals IR for different things along the way, such as deriving the voltage divider, right, and other things. And we also did a LED, or light emitting diode, right? I used green to show up, and we showed you, and then we combined some of these concepts. I think that's good, right? Right? This is your line, and even though these are all circuits-based concepts, in this class, it's not circuits as the end, right? That's the goal, the assignment to solve the circuit. These are things that you are being given, that are in your pocket, that you could pull out as you are undertaking design problems, right? And with that in mind, and I wanted to set it up very specifically this way, I wanted to give you another tool, which is the operational amplifier. Someone said yes? Yeah? You're excited for this part? Oh, like this, like, oh no. Yeah. All right. Here's why. In circuits, when you learn about operational amplifiers, it is an assignment. It is a complexity, right? It is one more problem that you need to learn how to solve. But in this case, in this class, it is a tool. And I will show you how to use it as a tool. I will show you how to use it in the simplest way possible. And I will rely on my favorite equation, Ohm's law. That's right, just Ohm's law. So if you're good with this, you're going to be good with operational amplifiers. They don't ask for more than that, though they seem to be taught that way. The first reason operational amplifiers seem intimidating when they're taught is a triangle symbol is used, which right away suggests some additional form of complexity, right? They're not actually triangles. There's nothing in your circuits box that is a triangle, right? But it is useful because in the way they are used as a tool, there's an input side and there's an output side. And an arrow is a nice way to remember it. But they're not triangles, all right? There are two inputs. One is called V positive and one is called V negative. In the actual, to be clear, right? In the actual thing, this is a square, and it might have 8 connector pins on it. And here you have V plus, here you have V minus, and then here I'll put in another pin, which is VO for V out. Right? 2 inputs, 1 output. And the inputs and the outputs are related by a straightforward equation. V out is equal to some, I write it out, some gain, which is a number, times V plus minus V minus. So for example, if put example, go to our hot pink. If the gain was 10 and V plus was 0.1 volts and V minus was 0 volts, then the output would be 1 volt. And that's what operation, and so that's the operation means they do something, and the amplifier is related to this gain, that they make things bigger. And if you think about it, up to now, we didn't have a way to make things bigger. I mean, the voltage divider only makes things smaller. So if I said take a volt and make it into 2 volts, you had no way to do it. But now you do, right? You could take 1 volt, 0, and have a gain of 2, right? That's the first step. Now, it's a little, right? Of course, there's going to be some more nuances here, all right? Now, this chip, right? Chip or integrated circuit, right? Needs to be powered. Like your phone, like your computer, it just needs a power supply. And so we have an addition here, power supply, and the power supply is called VCC plus and VCC minus. So these would also exist somewhere here. Let's say VCC plus might be here, and perhaps VCC minus might be there. So you're connecting your 9-volt battery to the chip. So now we have 1, 2, 3, 4, 5, right? And finally, all these voltages are going to be considered relative to some other point on the chip, and we're going to call that ground. There are variations of this depending on the chip, but this is a good place to start. All right? But even though I've added stuff, I just want you to focus on V plus, V minus, and V out, and I want you to focus on this operation here. That's it. So far, so good? Okay. If I were to plot, I'll do it here. No, I want space here. Now what I'm going to do is I'm going to plot V out versus V plus minus V minus. All right, so that's a single term here. All right, so for a certain V plus minus V minus, let's go to orange. I'm not putting any units here. I don't know if it's easier or not, but I get some sort of value. And and what's clear, this is going to increase linearly, meaning this slope here, right, is the gain. And I know that as the difference between V plus and V minus gets bigger, so will the V out, right? I'm plotting this line. That make sense? But look what happens. What if V plus is less than V minus? So let's say I reverse the situation, and instead I do 0 minus 0.1. and I multiplied this by 10, well, in this case, I will get minus 1 volt, right? 0 minus negative 0.1 times 10. So this output can actually go negative. It's positive only when this is bigger than that, but not the other way around. And so I can also draw points in this direction. And if V plus is equal to V minus, let's say there are 5 volts and 5 volts, 5 minus 5 is 0. So the output is 0. And so that is that point right here. All I've done here is I've drawn a picture representing this equation. That's the only thing I've added. But I didn't put units in just yet, right? Because those will depend, right? So far, so good? All right. Now, one of the first pieces, the second piece that you need to consider is the following. This output will start to approach VCC plus. For example, let's say VCC plus is, let's say VCC plus is 20 volts, right? So here I'm at 10, right? And then I'll just show another example. We're going to do 0.15 minus 0 times 10, right? So now I'm going to get an output of we have some way to go here. 1.5 volts. Yet another example, 10 times, now I'm going to go to 1 minus 0 volts, right? Now the output is 10 volts. And then again, 10 times 1.9 minus 0. And I keep making the 0 just to make it easier. Right now I'm at 19 volts, right? Is that door still closed? You can see that as the difference between V plus and V minus increases, we start to approach VCC plus, right? That's what's happening here. You cannot exceed VCC plus. What that means is that when we get to here, 10, 2 minus 0, now we are at 20 volts. So we're pinned. That's right, this point here, right there. Now I'm going to add. I'm going to say 10, and I'm going to jump to 3 minus 0 volts. What will be the output in this case? Well, 3 minus 0 is 3, times 10 is 30, but we can't go to 30. We just can't go above that. So in this case, the output will be pinned at 20 volts. And as I keep going up and up, I can't exceed it. So I'm going to have to extend this line in this way. So at these points here, I can't go above the line. I'm pinned. Now you could say, what if VCC plus was bigger? Well, then it would be pinned somewhere else. But I'm kind of not putting any, I put my units here, but I've left this without units. So I wanted you to understand that this here is a simple governing equation, right? But I need you to understand that V out must be, right, less than, or let's say equal to less than, VCC plus, and also greater than VCC minus. What do I mean by that? It means that I'm going to draw another line point here. I'm going to label this as VCC minus. And as before, I cannot go below it. So once I hit it, I stay on it. So this is the input-output relationship of an operational amplifier. It's not that this isn't true. It's just that we have this additional appendage stuck to it. So for example, you can't have an output of 1,000 volts, right, if your VCC plus doesn't allow it, and it doesn't allow it. Is there a question?
So then is the gain a constant depending on the device?
Correct. So the gain is something that, let's put it here, the gain is something that the device comes with, right? So it has this gain and that gain. You with me? Okay. Now, if you've had operational amplifiers before, I think you're thinking, I don't remember it being this simple, right? There are more layers to the onion, okay? But let's build them up one at a time. We have this, we have this. Now the next layer of the onion. You asked about the gain. It turns out that the gain of these operational amplifiers is by design very large. So I want to leave these examples and consider a different example. I want to consider a different example where now let's put the gain at 10. I'm just going to write 10K for 10,000. In fact, it's greater than that, okay? But let's start with 10,000. Fine. Let's go back to the same situation here, where we had one input, which was V plus at 0.15. I haven't written volts here, but it's volts everywhere, right? The other input is 0. And so now the question is, what would we get? Well, 0.15, right, times 10,000, right? You might be tempted to say, what would that be? 1.5 kilovolts, right? You might be tempted to say that, except you can't, right? You can't get this high. You can only get as high as VCC plus, right? So in fact, we're going to be at 20 volts. We're pinned, right? We didn't get there, right? It's not that these rules don't work. It's just that we're in this regime here. Sure. Well, how about this one here? 10K, right? That's our new. I'll put the gain here, right? This is our gain. 10K, and now one input is 1, and the input is 0. So you might think, oh, we're going to get to 10 kilovolts. Nope. We're at 20 volts because we just hit that pin again. It's even more down in this direction. Okay. What about a negative value? Let me reverse these. So I'm going to say 10K, and I'm going to say 1 volt minus 2. Right? So I have 1 volt and 2 volts, right? So 1 minus 2. Well, if you do this calculation, you might say, well, 1 minus 2 is negative 1 times 10K, negative 10 kilovolts. No, right? What would we add instead? What would be the value instead? It would be, we would be here. So this would be VCC minus, which maybe I didn't write it. In our example here, we're going to make it simple. VCC minus is also minus 20 volts. So we're actually at minus 20 volts. We've swung the other way. Can we cut it a little bit more thin? Let's do another one. 10K. And now what I'm going to do is I'm going to say 1 volt. And on the other side, I'm going to put, let's keep it positive, 0.99. Okay, so that's going to be 10K times 0.01. Right? Now what's the output? Well, 10K, 1K, 100 volt. I did it right, right? 100 volt. Am I going to see 100 volt? No. It'd be 20 volts. How about one more example? I mean, it's 10K times, let's do 2 minus 2.1, right? So this is 2. This is 2.1. So I have 2 minus 2.1. So I'm going to have here 10K times negative 0.1. Now, you might think you're going to have minus 1 kilovolt, but you won't. You're going to be at negative 20 volts. Yeah.
What would happen to the circuit if you actually tried to do this physically? Would it bring up the op amp, or would it just?
It would swing. I mean, there is a limit of volt. Yes, with these particular examples here, with these voltages, you would be swinging between these voltages. I should also specify this VCCs. The VCCs are also specified by the op amp. You might not be, you might not even be at 20 or 20. You might have picked 10 to be more realistic. Okay, but either way, you're swinging. So what we're seeing is, with a high gain, right? With a high gain, it seems like we're either here or here. To be in this range, right? To be in this range here, V plus and V minus, they almost have to be the same, right? I mean, even in this case, they were almost the same, right? But not quite. They would need to be like 1 and 1.0001, or 0 and 0.00031, something like that, right? The only way we can be in this range, right, is because the gain is so large, right? Because we have a large gain. And that is in fact how op amps work. You say, wait, that doesn't strike me as very useful. It's like someone, so we can say in practice, if V plus is greater than V minus, then V out is at VCC plus, and if V plus is less than V minus, then we are at V out is equal to minus VCC minus. Or another way to draw it, if I were to go to redraw this, is I would redraw it like this. I would say here is our input output. Here is V plus minus V minus. Here is VCC plus. Here is VCC minus. And maybe I'll use purple. Well, I'll add some ticks here, just so we understand that it's a grid. But the output actually looks like this. Right? What I've drawn here is that we're either pinned at VCC minus, right? I mean, this could go on, but it's not relevant for us. We're either pinned at VCC minus or VCC plus. We in practice don't have this linear range, right? You could say, well, Professor, why would you even, well, we'll get there, right? But one step at a time. So in reality, when you're using operational amplifiers, because the gain is, because of rule number 1 and rule number 2, and the fact that the gain is large, this is the input output. If the positive is greater than the negative, we're at VCC plus. And if the positive is less than the negative, or the negative is greater, however you want to think about it, it swings wildly. Here's another way to say the exact same thing, and I'm choosing my words here very carefully. If you were to compare V plus to V minus, you were going to make that comparison. If you were to compare V plus to V minus, and V plus was greater than V minus, you would return a VCC plus. And if you were to compare V plus to V minus, and V plus was less than V minus, you would return a VCC minus. A comparator. It is a comparator that swings wildly from one place to another. And let me jump straight to how we would use. So now you have here op amp, but a particular kind of op amp, which is called a comparator. How do you make a comparator? You just use an op amp. You don't need to do anything. It is an op amp, right? If you just have it, it is a okay. Here's something you could do with. Let's go back to the example we always fall on. You have a resistor, a temperature-sensitive resistor, R of T, and at 25 degrees, its resistance is 1 ohm, and at 30 degrees, its resistance is 2 ohms. I'm going to keep going back to this example just because it's familiar, all right? And the numbers are simple. All right, work with me. I'm going to put this into a voltage divider. So as we've done before, I have a voltage divider. I'm going to use a fixed resistance. And I'm going to make this 10 volts. And I'm going to make this fixed resistance here 1 ohm. And this here, right, is our sensor. And so now we have V sub T. Now, because we've built this, we can say that, I'm going to write it right here, that V sub T in these two situations is what? Well, at 25 degrees, this is 1 ohm. So we have 1 ohm and 1 ohm. Right? As we talked about before, when you have a voltage divider and the resistances are even, the voltage is split evenly. So in this case, the voltage here on the output is going to be 5 volts. Right? 1 ohm fixed resistor, 1 ohm R sub T, right? So 10 volts, and we have a 1 ohm and a 1 ohm, so this voltage becomes 5 volts. When the temperature goes to 30 degrees, we have a new situation where now this resistor here is 2 ohms. So now I have 10 volts, 1 ohm and 2 ohms. So this resistor is now bigger than this resistor. And the way a voltage divider works is it divides the voltage according to who has more resistance. Because this resistance is now bigger, it will take more of the voltage. And I'm just going to give you the answer that this is going to be 6.7 volts. And you can look back at other examples when we've done this. So up to now, I've reviewed it, right? We're sort of, this is a big, okay. Now I'm going to do something interesting. I'm going to connect this. This is not a line under this. This is a wire, all right? I'm going to stick to this color. I'm going to connect this to our op amp. All right, I'm going to take this wire here, right? I'm going to drop an op amp into my circuit, and I'm going to run a wire from here to, right, the positive terminal of my op amp, right? But that's what I've done here. And I'm going to put a voltage right here. I'm going to call this, I'm going to put a battery supply right here, and I'm going to put that battery supply at, I'm just going to put it at 6 volts. And here, I have my new output. I'm going to call this VO. And now the question is, what will VO do? So let's walk it through. I want to start with this example here. So this resistor was at 25 degrees, therefore it was at 1 ohm. Therefore this voltage here was at 5 volt. All right, so that means I have 5 volts here, and I have 6.7 volts here. 5 volts, 6.7. So this is less than that, right? This is less than that. It's going to be 5 minus 6, negative 1. Right? So negative 1 is the input. what is the output when the input is -1? VCC minus. And let's stick to the same VCC minus numbers I've given before. Well, I'll write it out. So therefore, at this point, V out is at VCC minus, and let's just say that is at minus 20 volts. So when it is 25 degrees, 1 ohm, making this 5 volts, making this minus 20 volts. You're with me so far? And then this example has a reason, right? All right. What about if we go to 30 degrees? Everything we're going through right now is conceptual. I don't think there's not really any math. In fact, the only math I put up we're not even using. So I do want us to be okay with this conceptually. This is a conceptual idea, right? All right. Let's go to this example. The room warms up to 30 degrees. If the room warms up to 30 degrees, this resistor will go from 1 ohm to 2 ohms. And because it went to 2 ohms, this voltage here is now at 6.7 volts. So we have 6.7 volts here. All right, so now this is at 6.7 volts. 6.7 and 6. 6.7 is greater than 6. 6.7 minus 6 is 0.7. So we are here. And in this case, V out is at, I know it's crowded here, but it's at VCC plus is equal to 20 volts. Right? So this was, this is an actual line here. This was all the calculations we did, right? This was the calculations we did for this circuit. Yes? Right. So the question is, you're understanding how this is making a comparison. In the practical examples we've done in the lab components, you've noticed that things kind of fluctuate a little bit and they're not exactly stable. So let me return to that point as well. That's a great question, all right? Here on the board, there's no noise. Here on the board, everything is perfectly clean. In reality, it's not, right? So now we have a situation where if you are monitoring the voltage here and you see that it's at 20 volt, right? You might infer maybe that it's at 30 degrees, or you might infer that it's at, but of course, okay, well, let me do a final piece of it. Right here at the end, I'm going to add an LED. Now we have an LED. And now I want to ask one more question, so we're not done here. I want to ask a simple question, which is the LED on or off? Let's start with this second example. If the output is at 20 volts, remember, this is the point we're talking about, 20 volts, the current is going to flow this way. And so in this case, the LED is on. In this case, it's still a lot of voltage, right? But notice it's at minus 20. The current wants to go in this way, but the LED won't let it. So in this case, the LED is off. Ooh. So now we have built a circuit. We have used all our tools. Right? I was introducing them in order for a reason. And this circuit has a feature that at 25 degrees, the light is off. And at 30 degrees, the light is on. So now you can have a device which says, oh, right, light is not on, light is on. And in fact, you can get a red LED, green LED. You can have whatever you want here, right? Now, the question, of course, is, well, what about at, let's think about now additional values, values, right? We can think about additional values. What about if where squeeze it in here? Add it here. Well, let's just think about it. Let's say that at 35 degrees, it was 3 ohms. All right, at 35 degrees, it's 3 ohms. All right, now at that point, the voltage here will be something bigger than this value. And so VCC plus will still be positive, and so the light will still be on. Let me go the other way. Let me go to 24 degrees. So at 24 degrees, the resistance, I'm not sure what it will be, but it's going to be a little lower. All right, let's say it's 0.9 ohms. So this voltage is a little lower. So this VCC is still negative, and so the light is still off. It looks, the output looks, if I were to, it's sort of, so what happens is that as the temperature rises, it's off, 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 off. And at the exact point where this crosses 6 volts, the light flicks on. So this here, you pick. This was something that you can control. You could have picked 6 volts, you could have picked 5 volts, you could have picked 4 volts. And if you're following along, what this means is that you can make this light turn on and off at any temperature you want. If I said, no, 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 I want the light to turn on at 35 degrees, you would simply adjust this value. If I said I want the light to, so what I mean? So I could say it's a temperature meter for my son, right? I want it to not turn on at all until you get to 37, right? And then I want the light to turn on. And it's orange. Oh, orange. Maybe I need to do something. Now you know how to do that, right? All right. When at 37 degrees, when it's in my sun, I want an orange light to go on. At 40 degrees, I want an additional red light to go on. 2 lights, right? Up, 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 orange. Up, up, up more, orange can stay on. Now I want the red one to go on. 2 lights. That means there has to be 2 LEDs, right? Do you know how to do that? Turns out you do. What I'm going to do is I'm going to leave this circuit so I don't have to redraw it. Okay, so this is our original circuit. This was our comparator, right, that turned on this LED, and this was the scheme we wanted before. Go back to this point here and take another op amp and connect it to a different battery source. I'm going to just make up a number here. I'm going to call this 8 volts. And now, if I call this V out, confusing, but fine, V out 1, and I have V out 2. And to make it clear that the LED is a different color, I'll use this. Right? And so here we have LED number 2. This value here will determine when this goes on. And this value here will determine when this goes on. Now, how do you know which values there are, right? Well, that's the same math we've done before, right? That's the equation for the sensor, right? And then you have we've done that before in the equation for the circuit, right? You can figure out that at 20 degrees, we're going to use values. I don't know if these are the same values. VT is, I'm just using new values. Let's say it's 1 volt at 21 degrees. VT is 5 volts at 20, I'm just jumping around. VT is 6 volts at 30 degrees. VT is 6.7 volts at 35 degrees. VT is 8 volts at 40 degrees. I'm writing a little sloppy here. VT is 9 volts. The actual values don't matter, right? You could have calculated these based on the circuit that you made. For any temperature, right? This is the part we were working before. For any temperature, you know how to calculate the output voltage of your circuit. It's not going to be these values. It's going to be something else. But you have these values so that you know at 30 degrees is when you hit 6.7 volts. So if you set this to 6.7, this light will trip at 30 degrees. You know that at 40 degrees, or let's look at this, at 35 degrees, you hit 8 volts. So this light will trip as soon as you cross 35 degrees. So now you can make an instrument where the lights go on and off, right, whenever you want. You need the equation for your sensor, and you need the equation for your circuit. And if you think about it, if we go even back to the other example where it started with the motion sensor, if I said you have to make a motion sensor so that when it goes from like 0 to 10 centimeters, but when it crosses 5 centimeters, a blue light goes on, you could actually figure it out. Just, you have to think of that through a little bit, right? But you could actually make something where as they move forward, as they cross 5 centimeters, the voltage crosses a certain point, and that's when you trip your comparator, and you just need to put a thing on it. And just as a final point, let me add it in a different color. In practice, we are going to be putting a little resistor here, all right, to make sure that the output current doesn't exceed what we talked about that last time. We don't want the output current to blow our LED, and so you'll be able to figure out what this resistance is to make sure the LED goes on, but there's not too much current coming out of your op amp. Any questions on that? Are we on time? Yes. So it's a great question. Will these have the same VCC plus or minus? They may not. I want you to realize that this is a physical chip. This is a physical object with those pins. As a matter of convenience, you'd often be, if you have one battery, you'd be powering them up with the same VCC plus or minus. Also, these are usually not things you control. They're sort of set by the chip. And so if the chip says this is the VCC plus or minus that's recommended, that's what you would use. Yeah, you're thinking already ahead to how to convert this, right, into something actually that would exist on a breadboard, right? And obviously you could split again, and you can split again. So far, so good. If I didn't give you a follower, sorry, not a follower, a comparator, I don't think you could do this. I don't think you could have a light that just goes on and off. So I didn't introduce an op amp to make your life easier. I introduced an op amp as a tool to let you do something that you could not previously do. Does that make sense? And so you'll get comfortable with op amp.